Okay, show. All right. So this week's paper was on the evaluation of blood-based biomarkers as a potential markers of amyloid burden in preclinical Alzheimer's disease. And by the way, thank you everyone who signed up and contributed to the slideshow. So here are our table of contents, and I'll go ahead with the introduction. Everyone who did the slideshows, just get ready. It's gonna be the same as last time. I'll get to your section, then you can just start talking. So this study was based on obviously Alzheimer's and a little bit of background on Alzheimer's. I'm sure all of you have heard of it. It's the sixth leading cause of death in the United States now. And there's many implications that come with it. It's called like the lo long goodbye because there's changes in like memory. Um, there's overall it's just a really hard way to go. And it's a huge field of research in neuroscience right now. Traditional PET imaging to determine Alzheimer's pathology is expensive and inaccessible. So I'm pretty sure like one of our first or second papers, we went over PET. And if y'all remember, is basically injecting radioactive tracers into your body. And the machine itself, everything, you can't say it's the most accessible way to scan. So this study basically wanted to utilize blood-based biomarkers to be identified or at least narrowed down on the individuals that might need further screening. And here are just some statistics on Alzheimer's disease to give y'all like kind of a sense of scale. So 7.2 million people are living with Alzheimer's in the United States alone. I mean, that's a crazy amount of people just to think about. And like like I said, it's the sixth leading cause of death in the United States, but it's also the seventh leading cause of death globally. So it's not just contained within the United States. It's huge all throughout the world, and the numbers are only growing. Um, Another key thing to mention is that there are significant ethnic disparities. So as you can see, Black or African Americans are twice as more likely to have Alzheimer's disease or other dementias, but are only 34% more likely to get diagnosed. So they're twice as more likely to have the disease, but only 34% more likely to get diagnosed. That's an obvious disparity. And the kind of similar thing happens with Hispanics or Latinos, where they're 1.5 times more likely to have Alzheimer's disease or other dementias, but only 18% more likely to get diagnosed. And this issue is something that was also addressed in the paper as well. For the methods, Jaden texted me and he said he couldn't come today, so I'll kind of be going over a section, and then Flora, you can get ready. So the methods, in terms of study design and patient cohort, there were 224 cognitively normal older adults from the A4 preclinical Alzheimer's trial. And all of them were scanned using the PET and they were qualitatively analyzed the amyloid plaques, and they were also an SUVR scan. I think it's like a type of scan was done and it was seen that half of them were positive for amyloid, half of them were negative. Um, in terms of blood collection and processing protocols, because this study aimed on blood-based biomarkers. Blood was drawn in all 224 participants, and they did this blood draw in two ways, basically. One was a 2 hour um basically analysis, or like it was frozen 2 hours after the blood was drawn. And the other one had the other subset of blood draws were done 24 hours after the blood was drawn from the actual patient. And these blood draws were sent to two different I guess facilities, one called Shimadzu and the other one called C2N. And they both use two different MS softwares to, analyze it. Okay.
So basically for I had two methods, the statistical analysis and the exploratory pet savings analysis. So first of all, for the statistical analysis, the people started off using the ROC curve analysis. And this method basically checks how good the blood test is at distinguishing between people who do and don't have amyloid buildup on their PET scans. And like they use the main summary measure they used is the area under the curve, or AUC, and a higher AUC means better accuracy. And in this case, it was, I think, 0.8, and which is, and then because the range is from 0 to 1, and 0.5 is like quite a not a good score, but like 0.8 is very close to 1, so it was a good score with high accuracy. And they also ran like a multivariable logistic regression model to see if factors like age, sex, or a POE genotype affected the relationship between blood biomarker levels and the PET scan results. For this, they split ages into 4 groups, and used stratified bootstrapping, which estimates the variability by repeatedly sampling data and makes sure that each resample provides the original group proportions. And they also used fivefold cross-validation to test the model 5 times on different data splits for a more like reliable performance estimate. And this means that there is a reduced bias and gives like a better estimate of how well the test might work in the real world. And so for the exploratory PET scan savings analysis, the researchers looked into how useful a blood test for amyloid might be before doing a PET scan. So basically, they wanted to figure out how many PET scans you need to do to find like 1,000 people who actually tested positive, and assumed about like 30% of people would test positive in the first place.
All right. Forget what I said about doing the chat thing. If anyone has any questions about the introduction and the methods, ask now. If not, we can move on.
Well, I guess since I'm here, I'll give a little bit of a another quick synopsis as well too.
That'd be great.
So so kind of why this study was so important. Because I think we published it in 2023 or 2024, but it takes time to build up to these types of studies. So in essence, we have brain imaging, which is expensive, not accessible to almost anyone. To be honest, you really can only get like a true amyloid PET scan as if you're in a clinical trial. I don't think I really know too many people who could just go to their doctor and say, "Hey, let me get this amyloid PET scan." So they're super expensive, but they are sensitive, right? So that's kind of what we always have to go back and forth with. We have a sensitive measure, but it's not accessible to everyone. So how can we make it accessible? And that's where we got blood, okay? But we also want to make sure that what we're seeing in the blood corresponds to what's actually happening in the brain. And that is really pretty much the main reason why we did this study. So, and we looked at a bunch of different parameters, right? But that's the premise, right? These people got a brain scan, and we want to say, does the measurements of amyloid, and I believe we measured tau in this paper, I can't remember, does that correlate to the amount of amyloid that you have in your brain, right? So that correlation. But we also wanted to test to make sure that there weren't any like technical things involved in that. So that's why we had 2 different companies run the assay, right? So if something is repeatable, then we can believe it. And then processing time. So I'm pretty sure everybody in here is probably given their blood for something, right? And so if the blood was processed immediately, 2 hours after collection, or if we waited 24 hours, does that also change the outcome? So I just kind of wanted to kind of highlight that and reinforce that, because that was the purpose of the study, is to see if correlations in the blood match what's happening in the brain, and then processing time. And the reason why the processing time was so important is because you got to think about logistics, right? So the clinic could have been overwhelmed and they may not have gotten to your sample in time. Does that delay, that 20-hour delay, does it actually change what the readout is? So we wanted to test as many different possibilities to ensure that whatever our final outcome measure, it's kind of been tested and tried, and we can really believe what the measurements say. So I hope that was clarified a little bit of things. And then with the methods as far as like the statistical analysis, so I will admit we have a whole team of statisticians that do that kind of analysis for us. But a ROC curve or receiver under the receiver operating characteristic curve, that's a very traditional, normal way to determine if there's correlation between A and B, or if there's a correlation between patient group A and patient group B. So you'll see hopefully in the results, you'll see what those curves look like. And yes, the closer you get to one, the more perfect that it is. So you want something as close to one as possible. Anything away from that, think of it like a percentage, because we're thinking about probability. So if it's 70% accurate, actually in our field, that's actually not really good. We want something to be 85, 90, 99% accurate. Okay? So I just wanted to interject that. Hopefully that kind of gave a little bit better, a shorter synopsis, if you will. But go ahead to the results.
All right, thank you. That actually cleared things up a lot. And so yeah, for the results, Sami, you can go ahead first.
Okay, thank you. Um, oh, sorry, I should okay. So, as mentioned in the methods, there were plasma samples collected from 224 CN or cognitively normal participants, and these samples were analyzed through mass spectroscopy. So as Professor Winston said, appreciate that. There were two labs used for the ROC curve analysis, C2N and Shimadzu. So in both analyses, they were measured with ROC curve analysis, and they found the area under the curve for Shimadzu was 0.8 and for C2N was 0.76. And this is how accurately they identified brain amyloid PET status. So, as you can see on the right, those are the there's the curves and there's the line for specificity. On the right, it's actually the area under the curve. I know it's a little like a little backwards for how it is, but you can see that they're nearly identical from both analyses. So that shows that since we have two labs doing these separate analyses, it shows that the identification is actually similar in both labs, which means that it's accurate in terms of the testing. It's not like separate per lab. And then on the bottom, you can see we have scatter plots. So these scatter plots were of the plasma against PET standardized uptake value ratio, and they did that again for C2N and Shimadzu under protocol 2, which means that they did it for a 2-hour test. And you can see that there's a negative correlation between the plasma ratio and the PET SUVR. So lower plasma ratio values were associated with higher brain amyloid. So you can see that the orange showcase where the blood-based analysis were actually correctly predicted positive amyloid patients, and the green shows where the blood-based analysis correctly predicts amyloid negative patients. And you can see that there's a clear negative, a negative correlation because it goes down in a negative slope. And so what these scatter plots show is that it actually predicts it supports the predictive ability of the plasma ratio for determining brain amyloid, which helps in determining, properly predicting Alzheimer's disease. So these scatter plots are actually very important for this research studies purposes.
Thank you. So continuing on with the results, we're now looking at the differences between protocol 1 and protocol 2. So this is on the left side, you can see the demographic data for the subset. And you can see that the Alzheimer's risk gene was more common in the amyloid positive group, 23 out of 50, compared to the amyloid negative group, which is 11 out of 50. And then other things you can see is that the race and sex of the participants, most were white and 67% of the participants were female. And age, you can see the participants were mostly older and they had a similar average age of about 73 years old. And then both groups also had similar memory scores, as you can see in the MMSE and the CFI scores. 28 indicates that they had normal cognitive function, and the CFI scores were similar between both, showing that they both had similar memory complaints. And the right side, you can see the clinical biomarkers between both protocol 2 and protocol 1, which indicate how accurate both of them were. So you can see that protocol 2 showed higher levels of both amyloid beta 42 and amyloid beta 40 and a higher ratio than protocol 1. and the differences between both of them were more accentuated. So you can see in the amyloid beta 42 and 40 ratio in protocol 1, which is taken 24 hours post phlebotomy, they had a score of 0.072. Then protocol 2, which was taken 2 hours after, had 0.090. So basically what this indicates is that protocol 1 wasn't able to detect as many amyloids. So this basically, in other words, is saying that protocol 2 is more accurate and showing that processing the blood faster, the proteins were most likely better preserved, leading to more accurate results. And just as clarification, lower concentration is somewhat linked to more likeliness for Alzheimer's. Next slide, please. So again, continuing on with the results, again, you have protocol 1, which is taken 24 hours after the blood draw, and then protocol 2, which is taken 2 hours after the blood draw. So as you can see on the right, we have figure 3, which compares the accuracy of detecting brain amyloid between protocols 1 and 2 using the measurements of the test, which are amyloid beta 42, 40, and the ratio. So I believe it's the AOC curve, or the chart, on the left side of figure 3. So the sensitivity shows how well the test correctly identifies positives, and specificity identifies how well the test correctly identifies negatives. And the AUC is the overall accuracy of the test. So again, as I mentioned, the closer to 1 is better. So looking at the chart, you can see that on the graph, protocol 2 performs better in both sensitivity and specificity. And then as you can see on the right, the AUC of protocol 2, which was 2 hours post, was 0.8, which is more accurate than protocol 1, which was around 0.064. So this shows that processing within 2 hours led to better accuracy. And yeah, thank you.
All right, I'm Jeffrey, and I'll be going over the last part of the results. So the next step in their research was to determine whether the demographic variables like gender, age, their APOE gene status would improve the ability of the ratio of the two biomarkers to predict the amyloid PET status. So what this means that instead of just inputting the ratio of the two biomarkers, they'd also input the age, the gene status, and everything to get a better prediction, more accurate prediction based on their age group. For example, if you're at an older age, you'll be at a higher risk. So the model will be able to take that into account and say, oh, maybe they have this. So what they found is that with ages 76 to 80 were approximately 2.5 times more likely to have amyloid PET positive than participants aged 65 to 70, which makes sense because with older age, you're at a higher risk of Alzheimer's that we found. And the APOE gene, which is commonly associated with higher Alzheimer's risk, carriers of this gene were approximately 2 times more likely to be amyloid PET positive. So in the end, they found that even when they did include these demographic covariates into their analysis, it did not actually improve the predictive ability significantly, which really surprised me. It might be because maybe the ratio of the two biomarkers was already enough for the model to predict, or maybe there wasn't enough data to predict, for example, because there wasn't much representation in certain racial groups, for example, is one of the parts of the study. But the study does not mention their theory on it. So now let's talk about the efficiency. So 6,700 people would need to be plasma screened for 1,000 people to be identified for having amyloid plaques confirmed with PET. So that means we're actually reducing the amount of required PET scans by 5,700 or 85% in total, which is just crazy. And the financial effects are still being studied on this.
Hey, my name is Arnolf, and so the key implication for this study was that it shows that blood biomarkers can find subtle amyloid buildup, which helps in faster recruitment for these different Alzheimer's studies. For example, if they want to see how these people are going preclinical over time and studies want to study that, well, then they have a better method for faster recruitment and potentially identifying people who are at greater risk of Alzheimer's progression. Then there's also a decreased reliance on PET scans, which means that now we have a cheaper method, a more accessible method, and it's non-invasive because it doesn't really use radioactive tracers. And lastly, it makes preclinical treatments a lot more accessible, and that's always better because preclinical treatment usually means that it has a higher chance of accuracy than treating Alzheimer's down the line when the symptoms are already pretty toxic. Then on to the actual study and the mass spectroscopy methods different used. The first was MALDI or Shimazu. This method was better at finding true negatives. So basically, it's better at confirming somebody doesn't have Alzheimer's. And so it has low sensitivity, but high specificity. And the cool thing about this method is that it works for both 2-hour samples and 24-hour samples. Last, using this method, the study did find a composite score that could potentially serve as a new biomarker that's stronger than just this ratio alone. The other mass spectroscopy method used was C2N, which is better at finding true positives, so confirming if somebody does have Alzheimer's. For this reason, it has high sensitivity and low specificity, and it works much better with 2-hour samples than 24-hour samples. But in order to properly compare both spectroscopy methods, there needs to be a little bit more standardization because in the study, there were some pre-analytical errors like sample mishandling or blood sitting out, which may have affected the results. And lastly, in terms of future research, there is a potential new composite biomarker from Shimazu or MALDI, which is a smarter predictor. The composite is found by adding AB42 or AB40, which is the ratio that this study was about, and then APP669711/AB24. That is essentially the amyloid precursor protein. And so, if you add both of these together, you have one that's showing the toxic amyloid buildup, and another protein that's showing the actual protein that's becoming amyloid. So, by combining them together, you reflect more biological pathways in the production, which means you have a more comprehensive biomarker, which can reduce prediction error. And in order to better study this biomarker and see if it's actually feasible, we need to do more research across different populations because, as said above, the sample is about 92% white. And so we need to see if this works across different groups of people as well.
So this is more of like a conclusion rather than a discussion, but it basically says that the APOE gene variation, age, and sex, which are all kind of common risk factors for Alzheimer's, did not affect the predictions of the blood-based analyses. And as mentioned in the previous slide, all current Alzheimer's studies have been missing or like underrepresenting certain like races like Blacks and Hispanics, despite having the highest incidences of Alzheimer's. And the implementation of using blood-based biomarkers to identify amyloid plaques can make Alzheimer's screening more accessible.
All right. Thank you everyone who presented. Um, Before we get into like a slight discussion, Professor Winston, do you have any other things to share or kind of give us more context into this research?
No, I'm like actually very thoroughly impressed of the interpretation. I think everything was explained very eloquently, even highlighting the nuances of the study, because limitations are always going to exist, right? So one thing that I probably did want to reinforce was, sample number does matter, right? So this was what I would consider to be a very small sample number, only 200 patients. And so, yes, 92% of them were white, and that's unfortunately not uncommon, even with studies that are coming out now that are doing very similar work. Even with 1,000 participants, 95% of them are still white. So, and keep that in context of the political climate that we're currently in today. There was a push for a very long time to increase representation so we really truly can see, are these blood-based measures truly correlative what is happening in a person's brain, and are there factors, those what we call covariates like genotype, gender, or I guess I should say sex, sex, race and ethnicity, do those actually impact how sensitive and how specific these biomarkers are? And you may think that could be an easy question to figure out, but in essence it's not. We don't know the answer. So we're still actively working to increase our sample number, make it more representative so we can truly kind of assess how sensitive these biomarkers are across different racial and ethnic groups. It's been understudied question in the field, because I think people don't want to talk about race. They don't want to talk about ethnicity. Race is a social construct, but there are biological correlates that differentiate us into, the categories that we may identify with. So we want to make sure that as the research continues, that all of those things are being factored, because I believe all of us do want to be represented in everything that we do, whether it's science research or anything that you enjoy. So I think that would be like my closing remarks, that this work is continuing on. Thankfully, we do have a grant that is directly related to addressing this question. So there are large cohorts that exist around the country that are diverse, and we are actively trying to pretty much correlate if the blood measures correspond to amyloid pathology in the brain. So yeah, that's all I had.
Um, Before we get into any questions I pull from the Discord, also if y'all have any questions, feel free to raise your hand. And I'll call on you too. But one question I had for Professor Winston was, I guess I didn't do a lot of research into this, but the statistics on racial differences or ethnic differences in Alzheimer's, is that based off of like certain like not pathologies, but like certain differences in like different races like in our genes, or like where would that be stemmed from?
So that's a very, very good question, right? So the caveat is that Hispanics and African Americans are 2 times more likely to develop the disease. And we have to keep it a caveat, is that is from the cases that we know. So African Americans and Hispanics are also less likely to seek treatment or be diagnosed under primary care. So it's unfortunate. It's kind of like this double-edged sword, if you will. So African Americans, and we can also have a conversation about socio determinants of health, access to health care, access to clinicians that are accurately going to diagnose you with Alzheimer's disease. So we can go through a whole rabbit hole on why Black and brown communities have a higher incidence of it when it's diagnosed. However, they are underreported cases due to all those other factors that I just mentioned. And so when we're talking about diagnosis, we're talking about a patient is in a medical clinic, they have a medical diagnosis, and that then goes to an insurance company, and then that goes to Medicare. So that's how they're tracking these diagnoses. That's how we can kind of quantify that number, and they can stratify that data based off of race and ethnicity and a whole bunch of other categories. But I do think that that number is probably underpowered, because again, how many cases have gone undiagnosed due to lack of medical treatment, due to lack of access, due to, I don't want to use the word ignorance, but now I feel like more people are educated, but 10, 15 years ago, you may not have thought that, mama forgetting where her keys are was actually dementia. They could have thought it was something completely different. So the statistics are based off of what we can actually quantify, what's actually being diagnosed in a clinic. But I also believe that that number is also not as accurate as it should be due to, as I said, the access that I just mentioned.
All right, thank you. Um, since no one has any hands raised right now, I can go through the
There's a
previously given questions. So
there
one
was
question,
a chat. Um, so the composite biomarker. So when we're talking about sensitivity and specificity, um, in the field, what we found is that sometimes one biomarker isn't enough to make the correlations that we're looking for. So we are complex creatures, we are comorbid creatures. So APP, amyloid precursor protein, is a protein that everyone in this room needs. It deals with lipid metabolism, and high levels of APP are thought to be a good thing. But if you are familiar with the amyloid cascade or the amyloid hypothesis, APP, which is this vital protein that we need for lipid metabolism, cholesterol production, that gets cut into the toxic form of A beta. So if you have high levels of A beta of APP, excuse me, then the idea was that you are more likely to break that down to form amyloid, if that makes sense. And so when you quantify the ratio, then you can kind of normalize those findings a little bit better to get a more accurate reading, because the A beta came from the APP. And in that paper, we just discussed one ratio. In more recent papers that have come out, people have done ratios with amyloid and tau, or amyloid and GFAP, which is an astrocyte marker. So the goal is to look at markers that we know are associated with changes in disease and quantify different statistical ratios that increases not only its sensitivity but also its specificity. So it's a biological thing, but it's also more of a statistical thing. And that's kind of the goal at the end of the day, that if we can quantify two markers or we can quantify three markers at one time, then hopefully we'll get a better readout than just quantifying one by itself. Okay.
Awesome. And Madhav also had something to say in the chat if you
Okay. Makes me remember, the making of the violent brain. Oh yeah, absolutely. So kind of reinforcing this idea, the sociology of neuroscience, right? So in all aspects of science, I mean, I think it's very clear that these studies are based off of biobank samples. So the participants likely enrolled in the study 10 years ago, 5 years ago, but that was what people thought was okay. We just wanted people to be in the study. We just looked at them as individual numbers. And then when clinical trials started to fail, when even the therapies that do exist now weren't being representative across more other different groups, people had to take a step back and say, well, we can't just assume that this overly white population is going to be biologically correlative to someone who doesn't look like them. So there are biological reasons as to why we look different, why we have different hormones. And so I think that was something that just wasn't as appreciated as it is now. Now, keep in mind, I've seen multiple different studies that say that race, ApoE genotype, gender don't make a difference, but we have to continue to ask those questions to ensure that that actually is the case. Because if we too take the statistics to be fact, if African Americans and Hispanics are twice as likely to get the disease, there is a reason for that, and we need to figure out what that is.
Samian, you can also ask your question.
Yeah, sorry. So my question is actually, I'm directing a question from the Discord. It was related to the results I spoke on. So I kind of want to give my short answer and then I want to direct it back to you because obviously I'm not an expert on this. But so Shreya asked, since the blood test of the A beta ratio in the plasma, it showed good but not perfect accuracy. Like as you mentioned, it's not 0.85, it's not 0.95. It was an area under curve of 0.8.
Yeah.
So they asked, what steps do you think are needed to improve these biomarkers so they're fully able to replace PET scans or just accurately like determine Alzheimer's disease? And so they also asked, do you think that it's ever possible for these to ever replace traditional screening methods? So what I wanted to say was, I don't think we can necessarily improve these biomarkers, or at least that's what I think, because these are, I guess, these biomarkers are not really changeable in terms of our research. These are just actual biomarkers. These are plasma inside of ourselves. We're just determining how good these are at, accurately predicting Alzheimer's disease. But I wanted your opinion. What did you think we could do about, these, the accuracy of these results? Do you think there's any way to make these more accurate? How we can potentially use a different biomarker, a different ratio, or,
Well, I think that
what can we do with that?
I was pretty much gonna highlight that point right there. So looking at different biomarkers. So when we think about Alzheimer's disease and the what we call the pathological hallmarks, what is known to be the driver of this disease, it's accumulation of amyloid protein in your brain. And then the other one, which I recognize is actually not represented in this paper, is tau. So both of those markers together cause the progression of this disease. Okay. And again, I don't even remember if that paper was published in 2023. Like the science moves very, very fast. So now amyloid is actually not the hot marker to measure anymore. So I'll find a paper real quick and I'll put it in the chat, but you may hear of a marker called p-tau 217. That is the hot marker on the street. And so now from here on out, since we publish that paper, that every paper since then, they've identified this epitope of tau, and that seems to be even more sensitive. And we're talking in the 0.95 region, doing the exact same measurements, but just looking at a different marker. And then the FDA approved a blood test. I just actually gave a presentation on this earlier. They approved it in May, looking at the ratio of p-tau 217 to A beta 42. So apparently that combination is like the winning target for today, right? Science moves very quickly. Who knows? Somebody may come up with another marker and say, oh, this is now 0.99 more sensitive. So it's a quick moving field. And we're just trying to do the best we can with the tools that we have thus far. Do I think that blood markers will completely replace imaging? I do not. I think we'll get to a point to where a blood test is going to check 9 out of the 10 boxes. We still may do imaging just to just to make sure that we're on the right track, because I don't think anything is foolproof. Again, there are always exceptions to the rule. There could be some unique feature about a person that we never accounted for that could actually change the outcome. But again, if we take if we kind of think of us as a heterogeneous population where the majority of us are going to be the same, then we base our measurements off of that. And then sometimes we may look up on that exception that requires further investigation. But yeah, to your point now, the proteins that we measured in that paper are in essence now obsolete, because we didn't even measure p-tau 217. But now today, you likely can't even get a paper published if you don't measure p-tau 217.
Okay, thank you.
You're welcome.
Okay. I'm also redirecting a question from Discord. This is Tareem's. And they asked, I guess this is kind of a general question, but it's something we should know. Are there any other blood-based biomarkers being studied or used right now to your knowledge?
So there's usually a panel that we look at. So p-tau 217 is the hot one. Then there's another version of tau, which is tau 181. So tau, just like amyloid, it's a long marker, and it has phosphorylation sites along the length of it. So what has been studied is that depending on where that phosphate attaches to determines how toxic it can be. So tau turns in what we call neurofibrillary tangles. So just think of the tau just kind of balling up onto each other and forming like this globular structure. So where the phosphate binds, and the number corresponds to the location. So I think tau goes from 1 to 344. So p-tau 217 is the phosphate at 217. Tau at 181 is the phosphate at 181. So that's how we kind of organize it. And based off where that phosphate grid is determines how tightly that neurofibrillary tangle makes, and then that will determine like how sticky it is. Because if it's slightly twisted, then you may be able to clear, but if it's really, really twisted, then it's going to be stuck for life. So those are two of the tau markers. A beta 40, A beta 42, those are always going to be measured. And then we think about Alzheimer's disease. There's also neuroinflammation, which was also something that's not covered in this paper, but it's a well-known hallmark. So we have GFAP, which is an astrocyte marker. So that's supposed to be indicative of neuroinflammation. And then we have another marker called NFL, neurofibrillary light chain. So that's supposed to be just a general marker of neurodegeneration in general. So synapse loss, tau loss, amyloid loss. Apparently, when all of those changes occur, then you also tend to lose NFL as well too. So we have two taus, two amyloids, GFAP, and NFL. Those are the 6, I would say, hot markers that are pretty much being measured routinely and consistently across all the papers that are coming out as of late.
Hey, thank you so much for that answer. Um, I think we have time for one more question. If anyone wants to ask a question right now, either put it in the chat or raise your hand. If not, I have a question too. So.
Okay, I see. Go ahead. Sammy has his hand raised.
Yes, I mean you can go ahead.
All right, sorry, I didn't mean to steal your question there, but my question was I actually asked two, but I think my first one got answered. My second question was, so in this study we did two protocols where protocol one was 24-hour long of testing, and then protocol two was 2 hours of testing. And obviously we're not focusing on amyloid as much as tau right now, but
Mhm.
in terms of either tau or amyloid, are there any more ratios that could be tested between a time of 2 hours and 24 hours, like let's say 6 or 8 or 10 hours, that would be more like potentially more accurate than the 2 or 24 hours that we tested thus far?
That's a good question, and to be honest, we settled on those two times because we thought about logistics, right? So, say for instance, someone goes into a clinic, right? If it's a slow day, then they probably can process that sample within the 2 hours. But if you're managing a 3,000 person clinical trial, just feasibly, it's not possible to process that many samples within a 2 hour window. And the protocols that are traditionally applied across all the phlebotomy centers that work with clinical trials, 24 hours is the standard operating procedure, or the SOP. So we were pretty much comparing normal protocol procedure, 24 hours, to something a little bit more rapid. Because when we think about things, so again, these proteins are coming from the brain and we're looking at them in the blood. So we didn't know if this was a rapid release. So if we captured them early in the blood, was that going to change how well they correlated? And so, and given based off the paper, the timing may or may not have had an impact. So something like 6 hours, something like 8 hours, I'm pretty sure other people can absolutely test those, right? But if you think about a phlebotomist, if I go to work and collect samples for 8 hours, I don't want to process them 2 hours later. So that's kind of how we try to think about what would be most realistic if this was like in a normal clinic in Utah where they only have one phlebotomist working. You know what I'm saying? Because sometimes we are in cities where there are 5 people working and they have a separate staff that can do the processing, and that's money, right? Not all clinics are like that. So, and then also too, you just can't test everything, you know. So that's just what we decided to do, and I'm pretty sure there have been other labs that have tested multiple other time points, but routine processing is 24 hours. That's normal across all labs.
Okay, thank you. That helped.
All right, thank you, Professor Winston, so much for all the answers. Um, Now I can kind of go on to the capstone project timeline, as I know a lot of you had questions on that. Um, okay, so here we go. Oh, also before we go on, this is something I kind of announced before with like the YouTube video, but Consensus IA actually partnered up with the club. Like I wasn't expecting this, but they reached out to me. So now all of y'all have access to premium for a year, I think. And Consensus AI, if you haven't seen the video yet, is basically like any other chatbot, but it helps you narrow down on research really quickly. So I was talking to I think I was talking to a researcher at the Broad Institute, if y'all know what that is today, and he was telling me how the most important, or at least even just for high schoolers too, because like what Professor Winston was saying, science moves so fast, it's really hard to get, I guess, up-to-date literature reviews, or it just ends up taking too much time. And Consensus AI can be really helpful for all of y'all whenever you're trying to start pursuing research because it gives you literature reviews. It makes you literature reviews with and it only takes information in from credible cited research papers. And it gives you all the citations too if you need to double check or if you want to dive in deeper. So yeah, I highly recommend using this during your capstone project because I think it'll make it really more efficient and much more easier and accessible for all of y'all to get into a topic that you genuinely enjoy. But yeah, and here's a capstone project timeline. It's kind of like it's basically what I showed y'all at the beginning of this entire club. And basically nothing changed. So now that it's early August, it's time for you to decide your capstone project topic. And it can be it doesn't have to be something based off of any of the papers that we read. It can be something anything related to neuroscience. So whatever you're interested in, go for it. And I'm not trying to restrict you or anything. But in all the papers we read, we've encountered a lot of different methodologies, a lot of different statistical analyses, and a lot of different ways to, I guess, just approach science and research in general. So based off of those, you can kind of start to see how you might structure your research, how you might um start gathering data if you're going to do research, how you might write literature review based off on the type of vocabulary and the jargon that you've encountered. And um just as a reminder, the capstone project is going to be two parts. It's going to be a paper and a presentation. So you're going to write a paper, a research paper on or a literature review or a spotlight article, whatever you choose to do, and then you're going to have a presentation. So like a Google Slides, a Canva, whatever you want. And on the presentation, it's going to be basically a presentation you're going to give to me towards late September, and I'll record it and I'll upload it to our website for a virtual symposium. And that's basically for right now, this week, your main focus is going to be deciding a topic. And I'll send a form out that asks for what all of y'all's topics are by the end of, I think I'll give y'all until the end of next week. So you have around 2 weeks to kind of think over what topic you want to do. And of course, if you decide on one, you can start pursuing it immediately. And I guess this was a question I kept getting. Just to clear things up, the research can be one of three things, or not one of three things. It can be anything. And anything I like to categorize into three different sections. It can be a spotlight article where you review an article and actually write a critique or a review on that article. It can be a literature review. A literature review has a little more work involved where you go through all the recent and most important research papers on your topic in that subcategory of neuroscience. Or it could be an original research done by you. And for that, I'm not going to try to hold you down on anything. You can literally cold email a professor from a local university and start conducting research. Um, and that's really, I want to give you the independence to start conducting your own research. And for this, in terms of the USC club, all you have to do is write a paper and a presentation based off of that research. And another question I got was, if you do decide to pursue a research, does it have to be completely finished by the time of our deadline? And obviously, if you're working on with other people, that's no. So yeah, research doesn't have, don't be pressured to finish research. If you're gonna do research with someone else, if you're doing your own research, what I want for you to do by this deadline is basically just, even the paper doesn't have to be finished. The presentation can just be everything up to what you are doing at that moment. So don't feel pressured to finish your research, because research shouldn't move like that. And then here it says August 25th. I'm pretty sure it's gonna say, Professor Winston, are you available August 25th?
Should be. That's a Monday, right?
Yeah.
Oh my goodness. I think I start teaching on Monday, on that Monday.
Okay.
And I teach two labs back to back. Let me double check, but I think I'm available the week before, but yeah, Mondays I teach two labs back to back on that day.
Okay. All good. We can we'll figure something out, and um well, sometime in late August, preferably when the professors are available, we're gonna have a checkup meeting. And during the checkup meeting, it's kind of gonna be like a workshop or just like a Q&A where you get to ask the professors any tips on research. And yeah, that's basically it. I don't think it'll be too long. It's just up to you to show up and ask questions. And then
Yeah.
towards early September, this is like you're gonna be kind of finishing up your presentation by then. And I want everyone here to have their presentation done by September 15th. So I'll send out a form then too, and y'all can just submit the presentation through that. And then you can continue revising your paper as well. The paper is going to be something like a paper is going to be something for you. So obviously I'm going to try to help you alongside craft the paper and get everything done. But the paper itself is up to you. It's like everything here is basically going to your pace. So we're resources. You can always come to us and ask questions. But like I said, never feel like they're deadlines, because, or never feel like you have to get something finished before the deadlines, because I just want to have a collection of what you're doing at that moment, not rushed, but at your own pace. And then towards late September, we're gonna have like the presentation recordings, like I said, where you present your research, and I'll record it and I'll upload it to the website for a virtual symposium. And in early October, there we might have a live symposium on like Zoom. That's still like something I have to figure out because last year, I mean, any online symposium is really hard to get like set up. So it's not a promise, but I'll try my best to work on something we can do. And Consensus AI, they also said that they could help in some way if they could. So um no promises, but it's something I really want to do. So hopefully we might be able to do some sort of like Zoom meeting where each of you get to present in front of a bunch of people that are outside of our club and showcase what you've just been working on and the neuroscience that you love. Any questions for the capstone project?
It may be good to say, like, because how long are the presentations? How long is the paper? You may want to give those details as well so people can know how to prepare.
Yeah, great point. The presentations, I honestly think the presentations themselves shouldn't go too long. So, um, if y'all know what an elevator pitch is, that's what they usually tend to put those down under 2 minutes. I wouldn't say it should be necessarily as short as that, but try to keep it as a brief overview of your research. And then to the people who genuinely like or who want to dive deeper, they can start looking into your paper. They can start looking into your like the citations you have in your presentation. But
Mhm.
the presentation itself, it can be like anywhere from like 5 to 10 slides. Just make sure you can go through it in under, I'd say under 10 minutes. But that's like giving it a long time.
Okay. Yeah, because I was gonna say there are two kind of talks we have. You can do like a flash talk,
Hmm.
which is 5 minutes, and usually that's no more than 3 slides.
Hmm.
Or you could do a shorter length, shorter talk, which is 10 minutes.
Hmm.
And usually, even with a 10-minute talk, you probably will only have maybe like 5 or 6, even 7 slides.
Hmm.
So I think 10 minutes is a good framework so people, have an idea of what how to put together their project. So I think 10 minutes is reasonable.
Okay.
Hmm.
So we'll keep it as that. And for the paper itself, um, the paper can be as long as you want. And also depending on where you want to publish it, if you are pursuing chasing publication, obviously there's different parameters and like boundaries for you. So first off, just write a paper and after once you start wanting to publish it, you can kind of narrow it down. But for the paper itself, it depends on your research too. If you're writing a literature review, it can be like it can extend really long, like 10, 20 pages, even 30. But if you're writing a spotlight article, this is just going to be a critique of one paper. So it might not be as long. So basically for the paper, write everything you have to. And then afterwards, when you start chasing publication, that's when you can start tweaking around with like the actual requirements. Does anyone have any other questions? All right. If everyone has no questions, then I'll send out the attendance form in the chat, and that'll basically be it for this meeting. So um until the next checkup meeting for the capstone project, we won't have any other Monday meetings. Um, and I'll send out the precise date for that checkup meeting soon in an email. Um, and yeah, so I'll send out forms, I'll send out emails. I'll keep everyone in the loop with consistent emails detailing information about the capstone project. But if you need any help, if you have any concerns, or if you want to hop on a call just to talk about more logistics, feel free to. But thank you everyone for coming to today's meeting. Good luck on starting to brainstorm. Uh, good luck on brainstorming for your capstone project, and I hope everyone has a great week. 1 second while I paste the Google Forms link.
Mhm. And while he's doing that, so yeah, I just checked my schedule. Monday is the only day that I teach. I don't teach any other day but Monday. And then my class starts on the 25th. And I know y'all meet on Monday, so I don't want y'all to change your schedule if that's going to be too complicated. But yeah, I can meet literally any other day but on Mondays.
All right. There's an attendance form, and I might send out a Google form regarding like when y'all's availability so we can schedule that capstone project workshop a little better. But yeah. And Madhav, for like research with professors, I mean I get what you mean. A lot of us have all experienced that, like whether it be cold emailing or just trying to get into research. Um if you need any help, feel free to reach out to me or Professor Winston. Um And if there's a very specific research idea that you have, and this goes to any of y'all, if you have a very specific research idea that you want to pursue genuinely, but there's no resource for you in your area, then yeah, just reach out and we'll try to get you connected or something. But yeah, thank you everyone for coming, and please do the attendance form and then you can go. Thank you.
Thank you.
Thank you.
Thank you, everyone. Have a good evening.